So, okay, we shall start now. So, I hope the screen is really visible to all. Okay, so what we have studied till now, let's recap it quickly. Okay, so we have studied mm, the Galilean transformations. Okay, just a quick recap, and those transformations are given by x prime equals to x minus vt, y prime equals to y, z prime equals to z, t prime equals to t. But it is more convenient to write this coordinate as above. Okay, we will see how y, and so I must rewrite it like this as t coordinate like this, and if you multiply it by c, nothing will change. Okay, because c is just a constant. Okay, now x prime is equals to x equals to minus vt, x minus vt, and y prime is equals to y, and z prime is equals to z. So this is a transformation, that is Galilean transformation. And simply the inverse Galilean transformation can be similarly given as, this is my S frame coordinates and this is my S prime coordinates, and these are x prime plus vt prime. Okay, when you want to see what is the physics in the S frame given the data of S prime frame, y is equals to y prime, z equals to z prime. Okay, so this is also called the inverse Galilean transformations. Okay, so prime coordinates, so we had a S coordinate which is S frame, which has like this coordinates, this is y, and a time clock. Okay, and a time coordinate, a clock. And similarly we had some S prime frame, that is y prime as y prime I mean the prime coordinates z prime, and a t prime clock. Okay, this is my S prime frame, and we always conventionally take the S prime frame as moving. Okay, this is my stationary frame. Okay, and this is my moving frame. Right, so this much we have studied, and these are the transformation equations for it. And similarly, okay, gt Galilean transformations in interval form can be given as, in interval form can be given as, or can be written as, simply like c delta t prime, or you can remove the c because Galilean transformations actually use the fact that speed of light is different in different coordinate system. So you can just write, even in like using that fact, I mean that should be, so you can write it like this directly. Okay, if you don't want to include the c in Galilean transformations, that's perfectly fine. But you can do that in Lorentz transformations because the speed of light is constant in all inertial fields. Okay, so this is uh, so to maintain the consistency, let's remove from here also. Now it's fine. Okay, because the speed of light do change in different inertial frames in the Galilean transformations or Galilean relativity. Okay, and similarly, y prime is equals to y del y, and del z equals to del z. Okay, and from this, we see velocity addition rule. Velocity addition rule. Okay, in Galilean relativity, or say the Newtonian relativity. Okay, and it is, you just define some coordinates, some definition like velocity, it is in the x direction, and sorry, this should be the prime, the t coordinate. Okay, and you define like this, and in prime coordinate, similarly, you just prime all the coordinates, all the variables. Okay, so you can just, from the above equations, you can just rewrite them as like in x prime, in x direction, you can just write it like this. Okay, so I'm just revising things that you can remind everything and memorize it. These are equations which you will need to solve many types of questions. Okay, so these are the set of velocity equations. Okay, so these are the Galilean transformations, and for light, for particularly light, okay, you see in a moving frame, if in the stationary frame the speed of light is c, then in the moving frame the speed of light changes. Okay, suppose the speed of the light travels in only x direction, so it will not have any y or z components, right, in both frames. So this will be like transformation equations for light or a photon. You can consider anything that travels with speed of light. Okay, so this is about my Galilean transformations. Now we have derived in the previous class the Lorentz transformations. Okay, Lorentz transformation, and anyone remember about it, that how do they look like? So in S prime frame they look similarly, like suppose T prime is equals to T minus V by C squared and X. Okay, and in X prime is equals to X minus Vt, and Y prime is equals to Y, Z prime is equals to Z. These are my Lorentz transformations. And if you have done the question of my last class, the last question of my last class, that was to find the inverse Lorentz transformation, will be given simply by, it's just your v, the sign of v will be changed, or say this will look like this. Okay, you are just changing the frames from s prime to s. Okay, this will be primed coordinates now, so it will be given by this. Y is equals to y prime and z is equals to z prime, because there is only the motion is only in the motion of S prime frame is only in the x direction. Okay, remember, otherwise these equations will change a bit. Okay, but not much, there is a symmetry, that's it. Okay, the equations are simple. Where this gamma factor, well, this gamma factor, gamma is called Lorentz factor. Okay, this is A, Lorentz factor, and gamma is given by 1 minus v squared by c squared. You can also define a different factor, that is beta, that actually calculates how much is the velocity relativistic. You can define like this, then this will imply that gamma is equals to 1 minus beta squared. Okay, now more symmetrically, okay, yeah, I can rewrite these equations in more symmetric form, like Ct prime is equals to gamma Ct minus V uh, by C, and V by C we have defined as beta, right? So it is beta, and it was, wait a second, beta, yeah, it is just x prime because we have multiplied the C factor both sides. Okay, so sorry, it is not prime. We are just writing the Lorentz transformation equations, not the inverse Lorentz transformation equations. It is just x. Similarly, you can just write this equation as x minus v by c, divide by it, and you will see that again you can write it in beta form, but now in the ct. Now here there will be a ct, and similarly this will not be changed. Okay, this is in more symmetric form. Okay, now you see one thing, you can similarly in interval form you can write these equations as c delta t prime is equals to gamma c delta t, okay, minus beta delta x. Similarly, delta x prime is equals to gamma delta x minus beta c delta t, okay, and delta y prime is equals to delta y delta z prime is equals to delta z. Okay, now you can from this similarly derive the velocity addition rules. Velocity addition rules. Okay, in like Einstein relativity. Einstein relativity. And how will you do that? In the similar fashion. Okay, you just define again the same thing. This is ux, and this y is delta. This is uy. Again, this is z is, this is uz. Okay, and similarly in prime coordinates. Okay, you can define these things in prime coordinates also, where you will have the prime on both the coordinates and also the variables. Okay, so now you just go back to your equations of in the interval form, and you just divide them. Okay, take this form first of all, minus beta t c delta t. Okay, this is the thing. Now divided by delta t prime. Okay, delta t prime on both sides. Okay, what you will see is gamma delta x minus beta, okay, c delta t will be divided by this gamma minus gamma in the bracket. What it will be simply this minus v. Okay, I shall write it in beta form. It's beta delta x, right? You just have just divided it by wait a second, should I divide it by c also? Let's do this for now. We will check it. Okay, so gamma got cancelled and del x minus beta c equals to this. Okay, and delta t minus beta del x is this. Okay, you now divide like both above and below, just divide by delta t. Okay, in both numerator and denominator. Okay, so what will happen, you see, you just divide it minus beta c. Okay, it will remain as it is because delta t will be cancelled out, and here it will also be cancelled out. Now beta and delta x by delta t. Okay, so what you get is ux minus beta c, that is actually v, of course, upon 1 minus beta, that is v by c ux, and this is your ux prime. This is my velocity addition rule in the x direction. Similarly, you can find for like y. Okay, this will be similarly in the prime coordinate, it is this, and this will be right like this, and del t minus it will be beta del x, right? Okay, now there is a gamma here. You just divide it both sides like this, 1 minus beta del x by delta t. Okay, so it will be now 1 by gamma u y upon 1 minus beta ux. Okay, and you can simply write it like this. It was, yes, beta, so gamma, it is uy 1 minus v ux by c. Okay, can you check it is dimensionally correct or not? If it is not, something is missing. I mean that something should be c factor, but if it is not, this is the correct thing. And you can rewrite this as like this also. Okay, because we have to find the gamma. Similarly, uy divided by 1 minus ux by c. So, what is the difference? It should be c squared, right? V by c got cancelled. This is of same dimension. There should be a c square factor. Let me see, check it again. Okay, this equation is not correct here. You have to consider the c square part also, because if we had the equation like t prime equals to t minus v by c squared x, and we then multiply it by c, that's why here came like this, but I should also include that by c here everywhere. So to make it consistent, you just divide it by c, and then it will be like c squared. Now it is dimensionally correct. Similarly, you can divide it by c here, or you can just do the calculations by not writing things in the beta form but explicitly in the v by c form. Okay, so this will be like this. Okay, now it is correct. Similarly, you do for this z prime. Okay, you will get a similar form: 1 by gamma u z by 1 minus v u x only, and you will get this. Okay, let me write this like u z prime. Okay, and this will be the equation. Again, here there should be a square. Okay, so these are my velocity addition rules in the Lorentz frame. Okay, and you just check the slow limit. In the beginning of this course, I have told you that Galilean transformations are just a special case of Lorentz transformations. Okay, Galilean transformations are just special case of Lorentz transformations. Okay, and what is that limit? What is that spatial limit? It is spatial limit is slow motion limit, right? And that is v is very less than c. Okay, so in the above equations, okay, suppose let's take the Lorentz transformations itself. So you take this, okay, gamma x minus vt, where now you have the gamma here 1 minus v squared by c squared, and in this limit, okay, when you take v very small than c, or say v tending to 0, okay, your gamma will be 1, right? And this will imply that your Lorentz transformations of x coordinate has converted into your Galilean transformation. Okay, and similarly for t coordinate also, your yes. So why t coordinate? Because gamma is 1, and this is v by x, v by c squared x, so this will also be neglected. So you can say in this limit, this is simply your Galilean transformations. Okay, now for light, of course, this should also work for light. Like uh, for velocity additions, okay, I have this ux prime ux upon 1 minus v ux by c squared. Okay, take this limit, v is very smaller than c, or say v is tending to 0. This will imply ux prime will be equals to Okay, is there a gamma missing or something? Okay, I have missed something. Okay, okay, I understood that. There is something. Yeah, minus v also. Yeah, minus v, and it will be like u minus. It is a Galilean transformation again. And for u y prime, you can see from here. This is my u prime, u y prime, and this will be again neglected, and your gamma will be 1. So uy prime will be translated to uy and uz prime. So this is my velocity rule. Again, we have reconciled reconciled velocity addition rule of Galilean relativity. Okay, this is not general relativity, this is Galilean relativity. Okay, I think you understood this. So suppose for light, okay, in Galilean relativity, we had a problem like we had a problem like that speed of light changes in different inertial frames. Okay, but in Lorentz transformations, and how does it change? You can see, of course, if your speed of light is constant, that is c in that is s frame, and you will get in s prime frame the velocity will be u minus v. Okay, or you can say u plus v when the direction of motion and the direction of speed of direction of propagation of light is opposite. But in Lorentz relativity, or say not in Lorentz relativity, it is Einstein's relativity. This is prime. Okay, c minus v, c plus v. You can say it like this. So in Einstein's relativity, okay, we have Lorentz transformations. Speed of light should be constant. Okay, so let's check from the Lorentz transformations. We have this minus v 1 minus ux v by c squared, right? So let's take in ux as v as c minus v, and this is cv by c squared, and v is again c, not c, sorry. Yeah, it is correct. V is just the velocity of s prime frame. So it will be cancelled out, okay? And you can see by taking the LCM, okay, this you will get this form c minus v, and this will be cancelled out. So this will be like this. So this is the velocity, or say the speed of light in s prime frame is also c. So it doesn't check. Okay, so my speed of light is constant. Speed of light is constant in different frames. Okay, observed from different frames. So this is fine, and you can check for above cases different in different directions also. So this has been verified that speed of light in Einstein's relativity remains constant in all inertial fields. Now let's come to some notions of like simultaneity and other things. let's pick up the Lorentz transformations again and see what can be the other consequences of it. As other consequences, other interesting consequences. Okay, you just take the interval form, that is del t prime is equals to gamma del t prime minus v by c squared del x prime. Okay, sorry, there's no prime here. Okay, it's fine. And again, for x prime minus v del t prime. Okay, and let's just take these two only. And you can see, you can define something that is called colocality. Colocality, that is two events, E1 and E2 happens at same location. That is called colocality. Two events happens at same location. And simultaneity means that two events, E1 and E2, happens or occurs at same time. That is simultaneity. In Galilean transformations, we have seen like our this was this, okay, but this was this, like our x coordinate was changing. So of course there is some relative, there's colocality if I mean if two events. Sorry, let me write it neatly. Okay, I'm really sorry about my poor handwriting. Okay, but the concepts need to be cleared. So yeah, in Galilean transformations, this is my equation for x coordinate, this is my equation for t coordinate in the interval form. And when you see, if you put to like del x equals to 0, and this will imply that my at del x equals to 0, this will imply, what will it imply? Will the del x prime will be 0 or not? If del x is 0, if the two events are co-local. If they happens at the same place. So of course this depends, this will be like depends whether you are defining your del t coordinates or the time interval as 0 or not. So it will be dependent on this. So it will be not co-local, of course. Okay, so it will be not co-local. Okay, but means not co-local in S prime frame. But when you see, when del t is equals to 0, this will imply del t prime is equals to 0. So if they are simultaneous in one frame, they will be simultaneous in S prime frame, the moving frame also. So from here in GT, if two events are co-local, then it will not be in moving frame. Okay, in general. But if two events are simultaneous in one frame, co-local. Okay, I should write this in one frame, that is stationary. Let me write it more clearly. In stationary frame, suppose. Okay, then then it will not be in moving frame, and in general. Okay, in general. But if two events are simultaneous in stationary frame, suppose. Okay, then it will also be simultaneous in moving frame. They should be simultaneous in moving frame. Okay, time passes. This implies time passes equally for all observers. This is about Galilean relativity. This is about Galilean relativity, which we actually observe in our daily life. Okay, this is true in our daily life, but at high speeds, but at high speeds, okay, that is v very greater than c. Sorry, not greater than c. I mean, it should be near to c, but always less than. Not always, yeah. In theory, not always. Okay, but at high speeds, okay, you see here, I have Lorentz transformations. I have Lorentz transformations like this. Del t prime is equals to del t minus b by c squared del x. Okay, when you put del t equals to 0, this will imply del t prime is not 0. Okay, this will imply del t prime is not 0. If they are simultaneous in one frame, it is not simultaneous in another frame. And secondly, if you have the second equation, okay, I forgot something, that is gamma. Okay, but in, yeah, del x minus v delta t gamma. Okay, if you put del x is equals to 0, this will also imply that del x prime is minus of gamma delta t. Okay, so means del x prime is not 0. So this is called relativity of simultaneity and colocality. This is called relativity of simultaneity. Okay, so Galilean transformations are not actually valid, okay, at low speeds also, but they are good approximation at low speeds. This should be differentiated, okay, correctly, because Lorentz transformations do apply at low speeds also. Okay, it's just that these transformations are approximation and could be corrected. These Galilean transformations are just an approximation and could be corrected by taking account the Lorentz transformations at low speeds. Okay, so Lorentz speeds are valid at both speeds, that is high speed or low speed or any speed. Okay, and Galilean transformations are good approximation at low speeds, but not strictly true at low speeds. Remind that. Okay. Now, so this is called the relativity of simultaneity and colocality. Colocality. this is O. Okay, this is also O. Co-locality means if two events are simultaneous or co-local, say this is or in one frame, then it will not be the same in another inertial frame. Okay, this is major consequence of Lorentz transformations. And people do usually say that this is the main reason that time is get dilated and length is get got contracted. But I see from the Lorentz transformations itself, from the coordinate transformations itself, it these RRS like from this interval transformations. Yeah. So this is the relativity of simultaneity and co-locality. Now again, if two events are both simultaneous and co-local, okay, then the event, then the events, such events, then such events are called coincident events. Okay, such events are called coincident events. Okay, now we have done the things. What else I have to do? Let me see. Okay, so we have defined the notion of simultaneity, okay, and co-locality, locality. What is this? And coincident events, coincident events. Okay, like you can write it like simultaneous plus co-locality is equals to coincident events. Okay, okay. We will study more detailed analysis about time dilation and length contraction in future classes. But for now, you can just write that del t prime is equals to del t by gamma or like this. Okay, and del x prime is equals to del x by gamma. How can you see that? From the equations actually define like, yeah. Okay, you make this del x 0, you will get this equation, and you make this delta t equals to 0 and you will get the gamma, but not actually I should define like this. Okay, uh, Yeah, from here you can see, you, you will see like this, and it should be confusing to you also. But del x is equals to del x prime by gamma. We will see how this is length contraction actually. Okay, we define some proper interval time. Okay, proper time interval, that is time interval in time interval in moving frame. Okay, and proper length, that is length, yeah, proper length or say distance, length interval, that is fine, in moving frame. Okay, so in moving frame actually the length is not get disturbed. I mean in moving frame actually we define like proper length as in the moving frame, because in the moving frame we see that in actually the length, if it is moving, okay, we define like this will be the proper length of the object in its own frame. Okay, and when you see from any laboratory frame, you will see some distortion in its length, that is length contraction, and that is how I define this uh, delta x prime as the length contraction, sorry, the proper length. I will come to it, okay, again, but for now I'm just defining it. Okay, we will see this. Let's define something else, that is uh, space-time interval. Space-time interval. Okay, uh, check this thing. You can check this thing, that uh, that is minus c t squared is equals plus x squared plus y squared plus z squared is equal to minus c squared t prime squared plus x squared x prime squared is equals to this. You can just check it by putting your Lorentz transformation equations, that this is an invariant quantity. This is an invariant quantity. This will not vary. This will be same. Why? This is simple. Why? Suppose I have a light source here. Okay, this is my light source, and it is producing some light wave fronts. Okay, it is producing some light wave fronts. Okay, now in the t time, okay, it will cover this O to P distance in the t time. Okay, in the, okay, so if we say that in the s frame the speed of light will be OP by the time taken by it, that is t. Okay, in s frame. Similarly in s prime frame, c, it will be c by second postulate. Okay, by second postulate it should be c, and it should be again O prime p. I take this in the O prime, this origin O prime in the S prime frame, and it is coincident. Okay, you can again say that it is uh, OP. It is similar, but in the S prime coordinates. Okay, so it will be T prime coordinate, and it should be same. So in the S frame, it will be like x squared plus y squared plus z squared. Okay, this is your length, of course, and this is T, and this will be x prime squared plus y prime squared plus z prime squared upon T. Okay, distance upon time is speed, and it should be constant. This is how you see, and these are both equal since the speed of light is constant. You can just equate them both. Okay, and you will find the above relation from this simple equation. Okay, that is T, and you just see that okay, this is T prime. Mm, wait a second, yeah, this is equal. You can square it both sides. Okay, I need to do one thing also. This is of course an invariant quantity. Okay, but also if you modify your above equation a bit, okay, this is suppose your first equation, and this is about your second equation. You just see like from the first can be written as c t squared equals to x squared plus y squared plus c squared, right? This will be given as minus c squared t squared plus x squared plus y squared plus z squared. It is 0 in this frame, and again by second you will get that c squared, it is t prime. So this will imply that in both frames these are 0 again, and you can say that this is also an invariant quantity. Okay, minus c squared t squared plus this. Okay, and this is important invariant quantity. We call it Lorentz invariant quantity. You see, it is not valid in Galilean transformations, in Galilean relativity, because the speed of light changes in different inertial frames. But it is Lorentz invariant quantity in the Lorentz Einstein theory. Okay, you can. This will imply you can in interval form similarly write this equation. So it will be given by c delta t squared plus delta x squared plus delta y squared plus delta z squared minus c squared delta t prime squared plus delta x prime squared plus delta y prime squared plus delta z prime squared. Okay, this is called the invariance of spacetime interval. Okay, and we define spacetime interval. Spacetime interval. Why are we calling it a spacetime? Actually, it is simple that from the Lorentz equation you can see from the Lorentz equations you can see that now I mean in the Galilean transformation the t coordinate was independent of x coordinate. Of course it was not like in boundations with this x coordinate, but in the Lorentz transformation equations, of course, the time in the s prime frame is dependent on the x coordinate of the s frame. Okay, so they are interconnected. Okay, they are entangled now. This time coordinate and the x coordinate are now entangled, and they both depend on each other now. So that's why Now the space and time are not separate quantity. Now the space and time are united, and we define that as space-time. In the Einstein theory, it is now space-time. It is a unique quantity now, and space and time are not separate things. So we define a space-time interval as this quantity, like this: del s square is equals to minus c squared del t squared plus del x squared plus del y squared plus del z squared. This is my space-time interval, and space-time interval is an invariant quantity. Is also Lorentz invariant. Okay, you, you can just define it. You can just like physically uh, think of this as the distance in the space-time. Okay, it is just a distance in space-time, just like any vector do have a particular magnitude, and no matter which frame you take it, okay, which frame you observe its magnitude, it will be invariant. Okay, just like this in 3D, in three dimension spatial dimensions. Okay, just like any magnitude can be defined like this. Okay, I mean, if you don't take the square form first, okay, you will see that magnitude will remain same. Okay, this is magnitude of vector. It will remain same, and when you square it, it will not affect it. Okay, but we usually take similarly we take like this as the space-time interval. We take this square form because it is more convenient to see the causal structure of space-time. We will see what it means, the causality. But first of all, let's just say that this space-time interval is actually an invariant quantity when you do the Lorentz transformations. Okay, it's a Lorentz invariant quantity. Okay, so okay, let's do finish it now. This is my space-time interval. We will talk later on now about it. Let's end the class today. If you have any questions, you can ask me in the comment section or say the WhatsApp group. Thank you. Okay, it is a very important quantity, space-time interval. We will see how what is actually it is giving us about the causal structure of any space-time. Okay, thank you for now. You can leave.